So welcome everybody. My name is Laurent Pinchard. For those who don't know me, I'm the founder and company owner of IDs on Board, a Linux contracting company specializing in multimedia development. And today we're going to talk about libcamera, which is a project that we have started a bit more than 2 years ago now. Because the talk is live, feel free to ask questions during the presentation, and I will make a best effort to address them, either directly, I'm watching the chat as I speak, or possibly if they will be addressed anyway later in the presentation, well, at a later point. So jumping directly on the subject, let's see if this works as well, or if there are issues sharing the screen. There we go. Can everybody see the slides? Perfect, amazing. There's even feedback, wow. All right, so very briefly, for those who don't know about libcamera at all, or have very little information about it, I'm gonna explain why we've started this. So as I mentioned, it's a project that's about 2 years old, but it's attempting to solve a problem that's much older. So in the very beginning, and I'm talking about more than 10 years ago, with the V4L and V4L2 API especially, hardware was quite simple. So we didn't have much trouble. We usually had a camera sensor that was attached to a simple camera interface on the SoC side, possibly with a bit of hardware to handle format conversion and scaling, and that's it. So that was fairly simple. You would have a V4L2 video node that's created by the driver that could be opened by any V4L2 compliant application, and you would be able, to capture from your camera. It would work exactly the same whether the camera was a PCI capture card, a USB webcam, or an embedded device that has a similar architecture to what's shown in this slide. So there was a single API to use, and all applications that were compatible with that would work properly. But then things became a bit more complex. What you're seeing on the screen right now is the block diagram of the OMAP3 ISP. So that's a device that's more than 10 years old now. That's what I've been working on during the Nokia N9 and N900 days. The device was more complex, and we had needs for a more complicated API to expose all its features to user space. So what we did was to extend the V4L2 API, exposing internals of the device to user space, creating a new API called the media controller. And well, that became messy because all of a sudden, you had quite a few device nodes that you had to open in user space, and you had to coordinate all those devices together. So from the point of view of a standard camera application, that became much more difficult because you had to deal with device specifics in user space and new application. So we had ideas at the time. Everything was supported, of course, on those devices we were working on with the custom GStreamer pipeline that was specific to the device. But we also had ideas of extended the libv4l with a plugin infrastructure that would allow implementation of device-specific plugins to support all that. But quite quickly after, well, you all know what happened with Nokia and the decision to drop the Linux mobile phone lines. And then, well, nothing happened. That never got implemented. We were left with the kernel side of the solution available in the kernel, but nothing in user space. But 2 years ago, we decided that something had to be done about that. The situation was becoming too messy, too complicated. It was really becoming a bottleneck, or a problem for vendors, for device vendors, for SoC vendors, for users, for pretty much everybody. And that's when we decided to create this brand new project called libcamera. Never been really good at coming up with catchy names. So this one may not be very marketing friendly, but at least it should describe properly what the project does. So libcamera is an open source camera stack and framework for Linux, Android, and Chrome OS. We're targeting, it's very important, we're targeting not just Linux desktop applications, but the whole Linux ecosystem. And we're focusing, and it's been a big departure compared to what I was used to doing. We're focusing on the user space side and not on the kernel side of the problem. So the high-level overview of this new camera, this library, and this new camera stack, it can be split in 3 or 4 different layers. At the very bottom, you do have the kernel layer. So as I mentioned, we're not focusing on that. We're using the infrastructure that exists today with V4L2, with the media control API, with all the devices that the kernel exposes, with all the existing drivers. That's a theory, at least. Of course, during development, we uncovered bugs in drivers or limitations in the APIs that had to be fixed, but it's definitely not the main focus of the project. On top of that, we have libcamera, which is really the core of the framework. So it's a library that can be used directly by applications. But we have also decided to have an additional layer called the adaptation layer, the libcamera adaptation, to offer compatibility with existing video-related frameworks. So we have an implementation of a GStreamer element that can act as a camera source. We have an implementation of Android camera HAL, so that Android devices can use libcamera as a camera provider. And we also have a V4L2 compatibility layer, which I'm going to talk a bit later in this presentation, that offers compatibility for native V4L2 application. The goal is to get them to work unmodified on top of libcamera, not even knowing that they actually run on top of libcamera. Of course, we can have native libcamera applications. That's certainly a goal in the future when the adoption of libcamera will increase. And those can right now be written in C++ because that's a language used by the project, but we're working on language bindings, Python, for instance, and probably others in the future as well. So what does libcamera, what does it do? I like to think about libcamera as the MISA of the camera world. So where MISA provides the whole OpenGL implementation and, well, and more than that in user space, we do handle all the features that an application would require when using cameras. So we start, of course, with camera device enumeration. So libcamera handles that part. It supports hot plugging as well, so it can detect new devices being added or removed. And for each camera that is detected, it supports, if the hardware supports that, of course, multiple concurrent streams from the same camera. One important aspect to consider here is that we're not talking about taking one hardware stream and multiplexing that, providing it to multiple applications. We're talking about hardware that can actually provide multiple streams from the same camera sensor with possibly different resolutions or different formats, but still all provided to the same application. When it comes to sharing a camera or sharing a video source between multiple applications, that's something that is out of scope for libcamera, and that is much better implemented in frameworks that would run on top, such as SpikeWire, for instance. We do support what is called per frame controls. So it's a concept that is well known to people who are knowledgeable about the Android camera API. But the idea is that unlike the traditional V4L2 device, where you would capture a stream of frames and would be able to set controls at any point of time, and then they would be applied by the hardware, I won't say randomly, but without being synchronized to the frames. Here, we have the ability to actually set controls and tie them to particular video frames, so we know when the control will be applied. So there's a much more precise and finer grain control on the cameras. libcamera, that's very important, has support for image processing algorithms. So what we mean by that is not the image processing itself. We still rely on the hardware, and especially on ISPs, image signal processors, to actually do the heavy lifting and process the pixels. But the way those ISPs work is that they have quite a few hardware blocks that will process the data, but they have to be configured. And they also generate statistics that are calculated for every frame. And the idea there is that you have to consume those statistics in user space, extract information from them, and then decide what exposure time you want to apply, what white balance gains and parameters you want to apply to be able to implement the auto exposure, the auto white balance, and autofocus algorithms, and possibly others as well. So it's really the control loop for the hardware that runs in user space. And in libcamera, we provide a framework where these tasks can be implemented in, so we call that image processing algorithm modules, shortened IPA modules. And they're loaded as external modules and external plugins. I briefly mentioned the fact that we have an adaptation layer. They offer backward compatibility with the existing APIs, V4L2 in particular, and allow integration of libcamera with other operating systems as well. So we do have implementations of those at the moment, but we'll dive a bit later into details of the implementation status of libcamera. So looking at how its architecture internally, well, again, at a high level view, it's fairly simple. Central to the stack, we have really two objects. We have a camera manager. That's really the entry point to libcamera. That's what you instantiate in the beginning. And that's a component that will enumerate all the cameras in the system. And will create camera objects that can then be acquired by applications in use. So the camera manager is the entry point, but it's not the most important object. The camera object is more interesting in the sense that that's really the central object that interfaces towards all the device-specific pipeline handlers. A bit of vocabulary, what's a pipeline handler? That's a device-specific part of the code that handles the translation between the standardized API that the camera objects offer to applications on one side, and the hardware-specific part, so mostly the communication with the kernel drivers. So if you think about what we call a camera pipeline, that starts at the hardware level with the camera sensor, then goes to a camera receiver and an SoC, for instance, an ISP, possibly other blocks, that's harder blocks that could be involved there, statistic generation, and all that. So the job of the pipeline handler is to really configure all those components so that they can work together. Another important part of the API is the camera configuration object. That's also quite central. I will not dive into lots of details about exactly how it's used here. If you're interested in getting more data, there was a presentation last year at the GStreamer conference by Jacopo Mondi, who's working with us on the camera, and who presented on how to develop a libcamera application. But the idea here is that application will create a camera configuration with per stream configuration and negotiate that with the pipeline handler until the suitable configuration that can be achieved by the pipeline handler that's suitable by application is found. And all that is validated internally and used to drive the camera. I mentioned already that the camera manager enumerates all the cameras. The way it works, the implementation we have today, is that it will enumerate all the media controller devices exposed by the kernel and try to match them with the existing pipeline handlers. This means that libcamera today requires kernel drivers to expose the media controller API. Not so much for configuration and management of the device at runtime, but at least for enumeration. So at the very least, you need that. Practically speaking, V4L2 is actually not a requirement. You could write support for camera and libcamera without using the V4L2 API if you have a kernel driver that exposes a different API. But because V4L2 is a de facto standard in Linux for camera support, you would have a hard time today upstreaming a kernel driver for a device that would use a custom API, for instance. So practically speaking, all the devices that we support, all the code we have uses V4L2. And so, I mentioned libcamera enumerate, the camera manager enumerates the media devices. It creates the instantiates the pipeline handlers, and those will register one or more cameras. So that means that depending on how the hardware is architectured, a pipeline handler may support a single camera, or may actually support multiple cameras from multiple camera sensors. You think, for instance, of a front and a back camera in a phone, and these could be possibly mutually exclusive if the hardware cannot capture from both of them at the same time, or they could be used at the same time. That's entirely hardware specific and handled by the pipeline handler. So the pipeline handler, as briefly explained as well, handles all the interface with the kernel devices and exposes then all the libcamera API towards the upper layers. It's the most complex piece of code that is written when you want to enable a new platform in libcamera, but we'll go back to platform enablement a bit later in this presentation. The image processing algorithms, a bit more about that. So I'll mention that, well, I'll briefly explain how they work. They're fully internal to libcamera in the sense that they're not exposed to applications. And that's the very big departure from what we had before starting the libcamera project, where I mentioned that all the device specifics, all the internals, the ability to capture the statistics, configure the ISP and all that were exposed through V4L2 extensions and through the media control API. And applications had to deal with that. Well, with libcamera, they're hidden internal, and so applications don't have to deal with it. We'll probably in the not too distant future have an API to actually make that information available, like the statistics available to applications that may need them, because you could still have device-specific applications that want to make full use of what the device provides, but it's definitely not required. The IPAs also mentioned that this is separated in modules that are loaded dynamically at runtime. And those IPA modules do not have access to kernel devices directly. So the architecture that we have mandates that they receive information from the pipeline handlers. That's mostly the fact that statistics have been produced, so they receive the buffers containing the statistics and other information as well. And then they run their control loop algorithms, and they produce parameters to configure the ISP, to configure the sensor. And then they send back those parameters to the pipeline handler that then deals with the hardware, with the kernel devices, and configures them. And that's fairly important because we mandate that the out of 3 IPA modules, and especially the closed source ones, will be sandboxed in a separate process. This is a requirement that came from the Chrome OS world, where they do not trust closed source vendor code, and I certainly cannot blame them for that. And always run that in a sandbox process that has limited access to the system for security reasons. Not so much because they fear that the vendors would ship malicious code, but just because they think it will be buggy and could bring the system down or actually create security issues because of bugs in there. And so we do the same. We do load those modules, the ones that are inside the libcamera source source tree and that's open source can be loaded without being sandboxed in a separate process. But for the other ones, we have an IPC mechanism that is transparent for both the IPA module and the pipeline handler that handles the communication with that external process. Not the most interesting part, probably from an architecture point of view, but we do have a fairly large number of helper and support classes to handle the media control API, the V4L2 API, to deal with with camera sensors, with threading support in the camera. We have geometry helpers, and we're constantly adding new ones as we need them, so that implementations of pipeline handlers do not have to reinvent the wheel all the time and can rely on known to be working, well, hopefully, code for all the lower level operations. Bit more about the V4L2 compatibility layer. So I mentioned it allows running native V4L2 applications unmodified. And the way we do that is quite similar actually to how libv4l2 operates, or how it can operate at least, is that we have a shared object that can be LD preloaded into the application. So it will override the libc calls, open, IOCTL, and map, and a few other ones. And if it detects that an application is trying to open a V4L2 device, then it will redirect that and all the subsequent calls on the same file descriptor to libcamera. So it's fully transparent to applications. It is a best effort implementation because it's not possible to emulate that way every single feature of every single device, and especially every single bug or quirk of every single device. But we've, for instance, tested that with Firefox, and have been able to place a video call using libcamera as the backend without Firefox being even aware of that. On the Android side, also mentioned, we have implemented an Android camera HAL component on top of libcamera. So it works for all the devices supported by libcamera. It's a single implementation, which means that if you want to bring up libcamera on a new device, you write a pipeline handler for your device, you write an IPA module for your device, but you don't have to touch the Android part. And so you get that more or less for free. Going to the topic of platform enablement, and I'm departing a bit from the ASCII art here because it would be completely unreadable. There's too much information. And I apologize if it's a bit difficult to read, but the details of all those blocks is not very important. What matters here is that at the lower level, so you have the gray blocks that are the hardware, and of course we don't deal with that. And then the blue blocks at the bottom, that are the kernel drivers. So we use them unmodified, V4L2 media controller. There's one thing to be aware of, especially for SoC vendors who would want to bring up the camera on the device. If you're using out-of-tree drivers, even if they're based on media controller and the V4L2 API, and if you want to mainline them, well, there could be changes that may be required to those drivers, but that's not because of the camera, that's just the usual mainlining process. And so on top, the core of libcamera is a set of lots of helper classes and standard objects that are in yellow boxes, and those are available to all the pipeline handlers. Can be used, they're not device dependent and don't have to be implemented. So the green part on the top right side is the pipeline handler itself. So that has to be implemented for each platform, and the complexity of doing so will depend on the complexity of the hardware. So we can't really say, yeah, it's easy, just a few lines of code. No, if you have complex hardware that needs complex operations to configure it, then the code will be complex. And on the top left side, in red, we do have the IPA module that is sandboxed. So there's also a set of helpers to handle the IPC and serialization of data. But the IPA module itself can be closed source, proprietary, or can be open source. We want to support vendors who want to ship a closed source implementation, not because We believe it's very good for either them or the community, but because all the vendors ship closed source implementations today, with one notable exception that I'm going to talk about. So because that's what the industry is doing, we realized that there was no way that we could push a new project and try to get it adopted by all the hardware vendors if we didn't give them a way to at least start with provide or continue shipping closed source implementation for the algorithms. The big difference compared to what's happening today on Android especially, where the complete implementation of the camera HAL is usually closed source, is that the pipeline handler, so the part that deals with configuring the hardware with all the plumbing, shuffling buffers around, passing them between different devices, between different IP cards and all that, that part is part of libcamera and is open source. That's not where the complexity of the algorithms lie, and that's not what vendors usually want to keep secret. But by having this split between those two different components, we can ensure that at least the hardware configuration part there is open. A few points that I want to emphasize. I already mentioned that we use the media controller and the V4L2 API, and so we do drive the standardization and extension development according to our needs. We've had to do that. It's been fairly interesting because I've been working on libcamera for maybe close to 15 years. On V4L2 close to 15 years. I've developed API extensions there, proposed them, upstream them, and when started working with libcamera and actually using the APIs that I have helped developing, I realized that they were really not well designed. So that's been a very good lesson for me, is that it's impossible to create a good kernel API if you don't actually have a real implementation in user space, not a test program, not a command line test tool or unit test, something that you write very quickly to make sure that it doesn't crash, but an actual real world user of APIs. But that being said, libcamera is a user space framework. It's not a hostile takeover of kernel development. So we're not we're really focusing on the user space side. Licensing, it's also quite important because we've had quite a few questions about that in discussions. So the kernel code, well, that's out of scope again for the camera, that GPL, and that's it. It's not a problem. The core of libcamera is licensed under the LGPL version 2.1 or later. That includes also the pipeline handlers. The IPA modules, however, can be closed source, and that's fully supported. So this means that you can write a closed source application linking to libcamera without any problem. You can write a closed source IPA module, that's not a problem either, but the rest is covered by the LGPL license. That means that changes need to be published according to the license, including for the pipeline handlers. But that's also a question we received from the vendors. They said, are we required to upstream those changes to libcamera? Well, that's not mandatory. The license doesn't require you to upstream anything, but we certainly highly recommend that because as for any open source project, folks are closely connected. No, perhaps a bit more interesting for people who have heard of libcamera before and knew more or less what it was. What's the actual status, and what are we working on, and what are we looking for the future? So first, what's there? That's a brief summary. The core supports multiple cameras, multiple streams per camera, per frame control, hot plugging and unplugging of cameras. So all those base features are there. We do have an extensive API documentation that we have started writing from the very beginning. Everything that is implemented is documented. It's been a bit painful. We are all developers and love writing documentation, but I think it's been very useful. We also have high-level tutorials and guides available, and we expect improvements in that area in the future as well. Because reference API documentation is nice, but without having tutorials and and high-level documentation that shows the big picture. It's very difficult to dive into. The platforms that we support today are Raspberry Pi 3 and 4. We support the Intel Kaby Lake and Skylake ISPs. We do support the Rockchip Arcade of V399, UVC cameras, USB. We also have support for the XP and XP MX7, and we have tested the Arena A31. The Raspberry Pi is really worth mentioning here because that's the best supported platform we have today, in the sense that the Raspberry Pi developers are contributing to libcamera themselves for everything else that's development that we have done in-house on our side. But Raspberry Pi is contributing. And not only have they contributed pipeline handler implementation and still contributing on that, but they have contributed an open source IP module. So the implementation of the algorithms, the auto exposure, the white balance, and all that is fully open source. It's part of the libcamera project, of the source tree. And that's, to my knowledge at least, the first and only product quality implementation of such algorithms for an ISP. So that's definitely worth mentioning. Adaptation layers, we talked about them already. We have a GStreamer source element that supports a single stream at the moment. We do have an implementation of an Android camera HAL for the version 3.3, which is not the latest, but brings most of the features. It has been tested mostly on, well, actually only on Chrome OS, because Chrome OS uses the exact same API for the camera as Android, so that has been our test platform. And we do have support for compatibility with existing V4L2 application. So I see a question regarding Raspberry Pi support. Does it rely on the VC4 driven drivers or native ones these days? So it's relying on native drivers. Well, mostly. So historically, Raspberry Pi had developed camera drivers that were kernel drivers and that were relying on a closed source firmware implementation. It's running on the VC4 that handled all the all that libcamera handles today in the pipeline handler and the IPA module and all the algorithms. They were closed source in the firmware. They have moved away from that. So the hardware for the camera is split in two parts. There's an EPC SI2 receiver. There's an open source driver now for that does not deal with the firmware at all. It programs the hardware directly. And then there's the ISP that operates in memory-to-memory mode. And so for that, we still have to deal with the firmware, but it's now a very, very thin layer that just receives basically the configuration parameters and applies them to the hardware. The only reason why it's required, to my knowledge, is that they're not allowed to disclose the actual register set for the ISP. That's a Broadcom product, and I don't think Broadcom allows them to do that. And so they have a very thin translation layer between the parameters that the hardware or the registers that the hardware exposes and the structure with parameters that we give them. But it's the same level of granularity. They don't do any specific processing there. They just shuffle the data around to program them in registers. And driver for that is the driver for the ISP. There's also a patch series that has been posted for the mainline kernel, and we're working and helping to upstream that. Tooling, that's also I think interesting. We do have a camera tuning tool that's been contributing by Raspberry Pi, and that's well, it's today specific to the platforms, but it's also an open source tool, and that allows camera tuning for a new platform or with a new camera sensor. We do have a tracing infrastructure that has been merged recently with a sample and trace analysis script that shows how to extract and compute statistics on the trace to, for instance, to try to find the outliers. libcamera is very heavily event-driven. This means that we do have event loops, and then we have to handle all kind of events, V4L2 telling us that the frame has started, that the buffer is ready, and all that from multiple devices. And so sometimes if there's a delay in one of those components, that can have implications on the real-time part of the algorithms. So being able to capture a large trace and analyze that to find the outliers, the places where once in a while there's a large delay, to try to figure out what happens is quite useful. We do have a few applications. There's an application very conveniently called CAM, which is a command line. We call that a Swiss Army knife application for libcamera. So the goal is really to have a low-level application that can exercise the whole of the libcamera API. We have a graphical user interface application called QCAM, with the Q framework. And we do have a symbol CAM application, which is also command line based, and that's our tutorial application. So we're trying to keep it as simple as possible, and it shows how to write an application that uses libcamera. What's ongoing now? Well, we're working on a few API extensions in libcamera itself, in core. Interesting one is what is called in the Android world the reprocessing API. So that means that when you capture a frame, you can capture it in the application and then send it back to the hardware for additional processing. And it can help implementing additional use cases. So that's under development. We are finalizing the IPA module isolation mechanism with the IPC. The patches have been posted, and they should be merged soon. There's work in progress to support the MediaTek MT8183 SoC, but only with YUV sensors to start with, so not with raw sensors in the internal ISP, but that's the first step. On the IPA module side, there's also work in progress to develop IPA modules, open source IPA modules for the Rockchip and Intel platforms, and that will be based on the Raspberry Pi code. We constantly add new controls and properties as they are needed, so I want to list them all individually. And we're also slowly going towards a public API free, so we're certainly not there yet. We haven't released version 1.0 yet. But the goal will be to freeze the API at some point with minor API changes that will remain backward compatible, pretty much like any open source project. And when we really need to release a new version that will break everything, that's going to be a major release. But we have also already started working on an extensible API design with design patterns that should make this easier to do and keep the backward compatibility for much longer. On the Android camera HAL side, we are running the CTS, the camera test suite compliance test from Android with different profiles. And so we are incrementally working on that to fix all the issues, or most of the issues that are reported by that. I mentioned that we support the HAL version 3.3. There's been a few extensions on the Android side with new version of the HAL. So that's on the roadmap. We have started working on the implementation of the required features in the libcamera core. But when it comes to the camera HAL component itself, it's currently on hold because we don't have a test platform that's with the devices that we support today, and that would allow us to test on that newer versions of the Android camera HAL. The reprocessing API inside the Android camera HAL, that will be started as soon as it's available in the libcamera core. And one of the interesting features that will be possible based on that will be the implementation of zero shutter lag. So zero shutter lag means that we want to minimize and bring to zero the time lag between when the user decides to take a picture and when the picture is actually taken. And if you think about a camera, if something happens and you want to take a picture, well, the first cause of delay, of course, will be the whole chain between your eyes and your finger touching the screen of the device, for instance, or pressing the button. And then there are other delays inside the device, and you may just simply miss the picture. We can certainly try to minimize delays at the device level, but the delay between your eyes and your fingers is something that is out of scope for the camera. And so the idea behind zero shutter lag is to continuously capture frames. And then when the user wants to capture an image, it's actually going back a bit backward in time to pick a frame that has been captured, well, a few frames before, to to bring the actual delay to zero. And the way that's then implemented is usually that you will capture raw frames and keep them in a ring buffer. And when an image needs to be captured, you go back in that ring buffer of raw frames, you take a raw frame, and then send that raw frame back to the hardware for reprocessing to actually apply the whole processing chain and have a YUV frame that can be used by the application. Few other things. There was zero shutter lag in the Android camera HAL. We could implement it there, but for applications that use libcamera natively, I explained how it's meant to be implemented, but you also don't want to force all applications to implement such features. And so we're thinking about kind of high-level use case library on top of libcamera that would implement zero shutter lag and similar features for applications. We are working on integration of libcamera in the Chromium web browser, and that's actually available on GitHub and successfully tested. So we have been able to place video call as well with libcamera in Chromium, which is quite nice. I mentioned already that there are Python language bindings that are under development, and I'm sure other language bindings will be developed later. And we're really trying to expand the community of users and hopefully developers. And so we have actively been supporting the community of people who own Windows-based Intel Kaby Lake machines. And that's, well, quite a few laptops, but also a whole line of tablets, especially the Microsoft Surface tablets that use that chip. And camera was not working at all for them. So now with libcamera, they have something that is not great yet. We don't have an IPA module, so images are not properly exposed, and they're usually very green or purple or whatever color, but not the right one. But there's ongoing development there. And that's an example of what happens with integration in Chromium. So on the top right side, you can see Jean-Michel, who's running libcamera in Chromium on Microsoft Surface Go tablet. And, well, I mentioned it's very green. So that's what you get with unprocessed images. And hopefully the work we're doing on the IPA module for the Intel platforms will bring the quality of those images to something that's at least acceptable. Roadmap for the future now. What haven't we started and that we're contemplating? Well, there's quite a few features. Some of them coming from the Android world as well, such as the first one, logical camera devices. It's quite common for phones nowadays to have multiple camera sensors on the same side of the phone. And for instance, a wide angle sensor and one with telezoom, teleobjective, telelens. Sorry. And when zooming, switching seamlessly between the wide angle sensor and the telesensor, so that you can have actual better zoom. You can also have power savings with that kind of mechanism. So we don't have that yet. We don't really have a platform that we can use for testing, but we will have just not started thinking about how to architecture. Still image trigger sequence. So we're talking mostly about focus and flash for this. This is also something that we haven't planned yet for the same reasons. We do have the concept of per stream control. So I mentioned that we have per frame control, but the controls apply to all the streams at the moment. So we have discussed the concept of having per stream controls as well. That's something that we want to have in the future, but we haven't started implementing it yet either. GPU-based processing would be quite interesting. We have a proof of concept shader code in QCam in the test application that is used to convert the format of frames that are being captured to something that can be displayed. And recently, this code that has been submitted to convert raw 12-bit frames to RGB in a shader. And that's something that we would like to leverage, possibly moving to OpenCL in that case, to be able to create a GPU-based ISP, or at least GPU code that could assist the hardware ISP with additional features. The last one I want to mention here is the exposure bracketing HDR. So it's a bit similar to zero shutter lag in the sense that it's a high-level use case on top of your camera that we could put in a use cases library, but also something for the future. On the integration side, we want to integrate libcamera in more frameworks, and we're thinking about expanding GStreamer support with multi-stream, integrating with Pipewire. Pipewire today uses V4L2 to capture frames from cameras, but as I've explained in this talk, that works for a subset of cameras that exist today, and many new devices, especially in the embedded world, but not only, won't work directly with that. So that's where libcamera would really fix this problem. Native integration in Firefox, now that we have Chromium, that would be nice. Integration in Qt Multimedia. I actually became aware yesterday that someone has written that, and it's outdated. The code is a year old, but it's available on GitHub. I wasn't even aware of that. So it's an interesting effort. We have libcamera support in Chromium, so that means that it will be available for Electron applications too. And whatever framework you may want to use, we'd like to support it with libcamera. On the application side, okay, I've listed Firefox both in the frameworks and application. That should definitely only be in the applications. And we really want to see way more native libcamera application support in the future. But of course, that will likely need to wait for the first public or the first stable release, because we don't want as a developer to maintain a set of applications on top of an API that changes constantly. On the operating system side, I explained that we are testing our Android camera HAL implementation on Chrome OS today. We're starting tests on Android as well. But we want to integrate libcamera and Linux distributions. We have support in Buildroot and Open Embedded already today. And so we want to expand that to make sure that it's actually shipped on devices and available for everybody. On the device side, new device support, well, we have a fairly small set of devices that are supported, and that definitely should be expanded. So we have ongoing discussions with SoC and system vendors with some informal commitment to work with us in the future. I cannot reveal the names at this point, unfortunately, but hopefully as soon as possible. And when it comes to open source IP modules, well, as part of the development we're doing to support Rockchip and Intel platforms, we will move some of the code that's Raspberry Pi specific today to a cross-platform core library. And so that could be leveraged to write more open source IP modules, and maybe with some community effort for platform-specific support on some platforms at least. I'm thinking in particular about the OMAP 3 ISP. I know there's still quite a few Nokia N900 and N9 lovers, and if someone could implement support in libcamera with a pipeline handler and IP module for those, that would be an amazing project. And then there's definitely long-term work to actually convince the device and SoC vendors that they should open source that code, but that will not happen overnight. I do believe that with the Raspberry Pi code that has been released, it's the first step towards a shift in the industry, but it will take time to happen. All right, that's the end of what I wanted to present to you. We have contact information as usual, so if you don't know the slides, we have development mailing list, we have an IRC channel, so feel free to contact us. And if there are more questions in the chat, I'm happy to answer them. So, merci beaucoup.